Hello friends, today we are going to discuss about the Mayer formula, or that is also known as Gaussian formula for spherical mirror, or there is also the relation between the object distance u, image distance v, and focal length f of a mirror. Sometimes this equation is also asked to derive the equation showing the relation between the object distance, image distance, and radius of curvature for a spherical mirror. That is the most important question because frequently asked in board exam. For that purpose, how we obtain this equation? For that purpose, first part is the description of figure. So how we do the figure? For that purpose, we do the concave mirror. That is the principal axis. Here, that is the concave mirror. Therefore, inner side is reflecting. This point is pole of a mirror. Pole. Okay. Now, here we place the one object, linear object AB on a principal axis of a concave mirror at u distance. Object is AB that is placed at u distance from the pole of a concave mirror. To obtain the image of this object, at least we require the two rays. Okay. Here we consider only the image of point A because the point B of this object is lying on the principal axis. Therefore, the image of B is always obtained on the principal axis. And one more thing, here the object is perpendicular to the principal axis. Therefore, the image is also perpendicular to the principal axis. Therefore, we have to only obtain what is the image of point A, and whatever the image we obtain of point A, we do the perpendicular on principal axis, that be the image of object AB. Okay. Now, to obtain the image of object AB, at least we require the two rays. One ray, which is parallel to the principal axis, incident at point M of a mirror. Here, the parallel is always after the reflection passing to the principal focus of the mirror. There is the principal focus, there is F, and there is the C. So after the reflection, this ray must passes to the principal focus. So there is the reflected ray of incident ray AM. Now we consider the another ray that is incident at point P from A. So that is the angle of incidence. At the same angle, there is the reflected. Therefore, the reflected ray is this. So another ray AP incident at pole of the mirror, and after the reflection is passing to the PA dash. Here at point A dash, the both rays are meet after the reflection. Therefore, A dash is the image of point A. Now, as we do a perpendicular on principal axis, so that becomes the image of AB as radius BS. So thus we obtain the image of object AB as radius BS. Clear this thing? Okay. Now, here the incident rays are axial, and also the aperture of the mirror is very small. For that purpose, we can say that this RPM as we consider as only a straight line. Only a straight line can be. Now, from figure, we assume that suppose the object distance dp is equal to object distance that is denoted as small p. Now, b dash p is equal to image distance that is denoted by small v. That is the small v. Now, what is the distance between the PF or the FP? FP is equal to focal length of a mirror, that is denoted by small f, and PC, that is the radius of curvature. And PC is equal to radius of curvature. Okay. Now the incident rays are backside and the aperture of the mirror is very small. And aperture of a mirror is very small, so that RPM is considered as a straight line. Therefore, from figure, here we consider the two triangles. One is MPF, this triangle, and second triangle is ADS, BDS, F are similar triangles. From figure, the triangles, one is MPF and triangle ADS, BDS, F are similar. Again, by considering the incident rays are biaxial and aperture of a mirror is very small, therefore this RPM or the NP is considered as a straight line. Therefore, this portion FPM we can consider as a right angle triangle. And after that, here these two right angle triangle, one is the MPF and second is the ADS, BDS, F are similar. Okay, now by considering this triangle MPF and ADS, BDS, F are similar, therefore this angle and this angle both are equal. Okay, for first we consider this triangle for triangle MPF. We take the tangent of this angle tan theta is equal to MP upon PF. MP upon PF. Now, for this triangle, ADS, BDS, F. Now, for triangle ADS, BDS, F. Again, this angle is supposed to theta. Therefore, tan theta is equal to ADS, BDS upon BDS, F. ADS, BDS upon BDS. Okay, now here left hand side of both equations are same, therefore compare these two equations. So MP upon PF is equal to ADS BDS upon BDS F. That is our equation 1. Similarly, here also these two triangles, one is ABP and also ADS, BDS, P are also similar. Similarly, triangle ABP and triangle ADS, BDS, P are also similar. Therefore, there is the angle of incidence, so that is the angle of reflection. According to the law of reflection, both are equal. As we consider both angles are theta, therefore we can write tan theta for triangle ABP. Tan theta is equal to what? Okay, AB upon PB. AB upon, here we take the BP or the PB. And for triangle, this triangle, ADS, BDS, that is equals to tan theta. Therefore, tan theta is equal to now ADS upon BDS, ADS upon BDS. Again, the left hand side of these two equations are same. Therefore, we are comparing the AB upon PB is equal to ADS upon BDS. Therefore, AB upon PB is equal to ADS upon BDS. Okay. Now, from this equation here, what is the MP? MP is same as the AB. In equation 1, from figure, MP is same as the AB. MP is equal to AB. Therefore, equation 1, AB upon PF is equal to BDS upon BDS. Therefore, BDS upon AB is equal to BDS upon PF. There is your equation number 3. And from 2, we can write the second equation in that form. BDS upon AB is equal to BDS upon P. That is our equation number 4. Okay. Now, last we have this equation BDS upon AB is equal to BDS upon PF, equation 3, and another equation is BDS upon AB is equal to BDS upon PB. Now, comparing equation 3 and 4. Comparing equation 3 and 4. Here the left hand sides are same, therefore the right hand side must be same. BDS upon PF is equal to BDS upon P. Okay. Now substitute the value with sign convention. Now BDSF in our figure, BDSF is obtained by considering the BDSP minus FP or the PF. From figure, BDSF is equal to what? PBDS or the BDSP minus FP. And what is the BDSP? BDSP is our image distance V, and that is the negative. Because our sign convention is that the direction of incident ray is from AB to MP. Here we are measuring the distance of PB in the direction of PBDS. So that is in opposite direction, therefore PBDS is negative, that is our image distance according to the sign convention, and the same as the BP. BP is the object distance that is also measured in opposite direction of incident ray, therefore the U is also negative. And also PF, that is the focal length of a concave mirror, that is also negative. Therefore, BDSP is minus V and PF is equal to minus F, and PB or the BP is equal to minus E. Therefore, BDSP minus FP upon PF is equal to BDSP upon PB. Now, BDSP there is the minus C. And here FP is equal to minus F upon minus F is equal to VSP minus V upon PB is equal to minus Q. This minus minus becomes the plus, and here minus minus becomes the plus. Therefore, minus V plus F upon minus F is equal to V upon V. Okay. Therefore, here V minus F upon F is equal to V upon U. Okay. Therefore, V upon F here minus here F upon F, that means the 1 is equal to V upon U. Therefore, V upon F is equal to 1 plus V upon U. Dividing by small v. Therefore, we obtain 1 upon F is equal to 1 upon V plus 1 upon U. There is a mere formula. Equation number 5. Equation 5 is known as mere formula or Gaussian equation. For spherical mirror. Or there is also known as the relation between the object distance, image distance, and focal length f of a spherical mirror. Now, this equation is valid for both types of the mirror. For our simplicity, we obtain this equation for the concave mirror. We can also derive the same equation for convex mirror. Oh. Okay, now what is the linear magnification and obtain this equation for the spherical mirror? First we discuss or we define the linear magnification. Linear magnification, that means the ratio of height of an image to the height of an object. Again, the definition of linear magnification is that the ratio of height of an image to the height of an object. Here, the height of an image is S and height of an object is H. Therefore, it's S upon H that is known as the linear magnification. It is denoted by small m. Therefore, m is equal to H dash upon H. Equation number 1. Okay. How we obtain this equation? For that purpose, here the figure is earlier same as here for a concave mirror. M is the linear object and the height is H, and its image formed by the concave mirror is ADS, BDS, and the height is HS. Now from figure, here the two right angle triangle, one is the ABP and second is the ADS, BDSP are the similar triangle because this FPA makes an angle theta, that is the incident angle or the angle of incidence, and the same way this reflected ray PA' makes an angle with the principal axis theta, that is the angle of reflection. Therefore, from laws of reflection, these two right angles are similar. Okay. Now, first for this right angle triangle ABP. Now, what is the tan theta? Tan theta is equal to AB upon BB. Here we have write down this tan theta is equal to AB upon BB. And now, for the second triangle ADS, BDS, this angle is theta. Therefore, tan theta is equal to ADS, BDS upon BDS. Therefore, tan theta is equal to ADS, BDS upon BDS. In this equation, left hand side are same. That there is the tan theta. Therefore, comparing this equation, therefore ADS, BDS upon BDSP is equal to AB upon B. Okay. Now we end this equation in that form. ADS, BDS upon AB is equal to BDSP upon B. Now, in this equation, we substitute the values with sign convention. Okay, now from figure radius, is the height of enemies. There is the below the principal axis according to the sign convention. There is the negative minus axis. There is the minus axis. Now second is the AB. AB is the height of an object that is above the principal axis, that is considered as positive axis. And also, now what is the BDS? BDS is the distance of an image from the point. So there is measured in opposite direction of incident ray. Therefore, BDS is considered as negative. There is the minus BDS. B is equal to minus. And what is the BP? BP is that means the distance of P from B from P. Therefore, there is the object distance. There is also measured in opposite direction of incident ray. That is negative. Therefore, BP is equal to minus. Substitute this equation. Therefore, minus H upon H is equal to minus B upon minus. Therefore, H upon H is equal to minus B upon U. Drop equation 1. That is M. Therefore, linear magnification M is equal to H upon H is equal to minus B upon. So, by knowing the height of an image to the height of an object, we can also calculate how much the image of given object is enlarged or contract. And also, by knowing the value of object distance and image distance, we can judge about the magnification of this type of the